Hello everyone and welcome back in our channel. Today we have another application for second order homogeneous constant coefficients differential equations. It's RLC series circuits. Here we have R, C and L, resistance, capacitance, inductance. And here our switch at t equals 0, we move the switch, we disconnect it from this point to this point. At time equals 0, the voltage drop across the capacitance V naught and the current in the inductor is I naught. Applying Kirchhoff's voltage law to the circuit, summation of voltage equals 0. VR plus VC plus VL equals 0. The voltage drop across the resistance is the current times the resistance, IR. And across the inductor will be all di over dt. And across the capacitor, 1 over c integration from minus infinity to 0, I d tau. Here we put tau just to make a difference from the time t. Still refers to time. And minus infinity, we see the situation before we disconnect the circuit, before we move the switch from this position to this position. This is why we meant by minus infinity. We derive this equation with respect to time. So here we have R, di over dt, and then all this is the second derivative, and the integration will be cancelled because we derive, and this is our equation. It's second order constant coefficients here, and it's homogeneous because the right side equals 0. We find the characteristic equation and here, and we have the three choices. Either this term is bigger, or this term is equal, or this term is less than this one. And every case, the first case will be over damping, and the second critical damping, and the third will be under damping. And I put it in every case in different colors. So here, and the second one, and here the third one. This is the general form of the complex number. In our situation, A will be minus alpha, because alpha always minus. From this, see, it's always minus. And we have example. Here the first example, R equal 40 ohm, the L 4 Henry, and the C 250 millifarad. And here is the initial conditions. It is exercise for the engineers to find from the circuit. But the other two examples, we have the current at time 0 equal N, and the derivative equals 0. And the third one is 10 ampere and minus 50 ampere over second, because we have di over dt. The initial conditions, they found it from steady state, and they put t equals 0, and then for the first one, the solutions here, alpha r over TL, 2L, so 48 will be 5, omega naught will be 1. So here's the case, alpha square is bigger than omega naught square. And the roots, lambda 1, 2 equal this one and this one. To find A and B, you insert the initial condition, whatever here, and you will get two equations and then find A and B. The second one, the resistance is 10 ohm, 140 millifarad. Here alpha equal R over 2L is 5, omega naught also 5, so they are equal. The system is critically damped. You know, this term will be 0, so lambda 1 equal lambda 2 equal minus 5. Here's the relation of the current. We use the initial condition to find A and B. Of course, when we put T0, this term will be cancelled, and we get A equal the current at T equals 0. And then we apply the derivative of the current with respect to time, which is given here also 0, and then we find an equation in terms of A and B, and we got A from here, and is A will be 10 and B will be 50. The third example, resistance 5, inductor 1 Henry, and the capacitor 1/9 farad. And the initial condition, I sub 0 equal 10, and di over dt at time 0 equal minus 50 ampere per second. Here is our solution. We found alpha, we found omega naught, and since alpha square is less than omega naught square, so this is the formula for this case. We put here the damped frequency equal this one. So this is the formula of our solution. Applying our initial condition here, the same procedure, but here we need to use the product rules because we have two functions. This function multiplied by the other function, which is cosine and plus sine. And here is B equal minus 15, 0.07, and A equal 10 when we solve this for A and B. Thank you for watching my video, and see you in the next video.